This is the second most misunderstood tuning option in RC crawling, right behind anti-squat. RC crawlers have been around for many years, and the quest for better performance pushes forward. There are, however, a few areas that are still in their infancy. The correct term for what we will explore is negative springs. You may know them by the street name Hairbands or pen spring mod. Despite being derided and despised by many, negative springs are widely used and loved, and they can be a valuable tuning tool for RC crawlers that want maximum vertical climbing capability. And unlike anti-squat on crawlers, negative springs actually work. Opponents of the concept point to countless world championships being won without hairbands. I would point to F1 and many other sports where you couldn't win on the equipment that was being run just 2 or 3 years ago. Opponents will also say that if you tune right, you don't need band-aids. I would ask, so what is this magical tuning that defies physics? And I get, do we still need to say like and subscribe? People know that, right? All right. On this channel, we look at the science behind our grown-up toys. I'm going to show you how negative springs work and the best way to set them up, and you can decide if you want to deploy them or not. First of all, why did people start using hairbands and pen springs? It was an effort to keep the front suspension from extending or unloading on steep climbs. It actually also applies to descending to keep your hind end from going head over heels. Another effort that people have tried is with suspension linkage, anti-squat, and link risers. I've made 3 videos that explain why that doesn't work on slow-moving crawlers. You simply cannot push or hold the front end down with any version of suspension linkage on RC crawlers. So that leaves us with negative springs. There are 3 prerequisites for watching this video. First, you need to know what a hairband or pen spring mod is. Second, you need to have an open mind. If you're already a hater, this may not change your mind. Thirdly, you need to understand preload and spring rate, so watch my other video. I suspect that part of the reason hairbands and pen springs are so maligned is because they seem bush league. They aren't elegant or sophisticated. You mean to tell me that a 14-cent hair tie that I can find in my wife or girlfriend's bathroom drawer is the key to climbing performance on my $3,000 truck? Absolutely. Also, there's not really a full-scale equivalent that we can reference. Full-size vehicles require some suspension to protect the engine and the driver, and the unsprung weight ratio is completely the opposite to that of an RC crawler. The closest thing I can think of is a suck-down winch. You certainly could put a tiny servo winch to pull down the front end, and I've seen it done, but a much simpler solution is a full-time negative spring. This is why I love RC crawlers. They have their own rules and their own opportunities. Also, most people are not setting up their negative springs correctly or at least optimally. But we're going to straighten all that out. So let's reframe this garage hack as a high-end performance tuning option. First, let's start with a quick refresher on spring theory. When your chassis is unloading, what's really happening is your shock springs are pushing the chassis away from the axle, away from the ground. Because the terrain is so steep, there is not enough chassis weight to keep the shocks compressed. That is combined with the torque coming from the rear wheel drive. Here's what a spring looks like graphically. As the shock and spring compress, the force goes up. In this case, we're looking at a 10 gram per millimeter spring. Every millimeter of compression requires 10 grams of force to move the shock. This is called spring rate, Hooke's law, and it is represented by the letter K. The mathematical slope of the line is the spring rate. Slope is calculated by rise over run. You might remember this from junior high algebra. This is also different than preload. This is what preload looks like. The line shifts up. The slope of the line, or the spring rate, remains the same. Preload does not make your spring stiffer, and that's explained in my other videos. There are 2 common types of springs, compression and extension. They look quite a bit different, but the math applies equally to both types of springs. You can pull on a coil spring and it will provide you the exact same spring rate as pushing on it. Extension springs often look a little different, but the spring rate formula will be the same. Extension springs are usually wound with the coils touching. This is simply to keep the spring short, if it's only extending, never compressing. Also, they will have different end treatments, like these loops that allow you to grab the spring so you can pull on it. Here's another way to visualize it. A 10 gram per millimeter spring with 20 millimeters of stroke. Each increment takes the same amount of force to move the shock. It takes 50 grams of force to move the shock 5 millimeters. That applies to both forward and backwards. It takes 50 grams of force to move from 50 to 75. Conversely, it takes 50 grams of force to move from 75 to 50. The next thing you need to understand is that when you put two springs together, you get a new compound or single spring rate. There are two basic ways to combine springs: parallel and series. This is a parallel spring arrangement. The springs are side by side, and the force pushes directly on both springs simultaneously. This is what springs in series look like. The springs are stacked, and the force pushes on one spring, which in turn presses on the second spring. This has a totally different resulting spring rate than the parallel arrangement. Here's the equation for parallel springs. You basically add the two spring rates together. This should make sense intuitively. It's harder to compress two springs than just one. Two springs, each with their own different K value, add together to equal a new K. I went to Monster Jam last week, and this is why all the trucks have two shocks. Twice the spring force to hold up these 12,000-pound monsters. Each shock only has to do half the work. And you can build much higher spring support with two shocks. This is the equation for springs in series, and to me it's a lot less intuitive. Think of it as pushing on a spring that's sitting on a trampoline. When you push on the spring, it also pushes on the trampoline. So you have two springs deflecting or giving way, which makes the response softer than each spring on its own. The equation for this is the inverses of the rates added together. Now let's demonstrate this theory on the workbench. I bought this gauge off Amazon. I will put an affiliate link in the description if you want to purchase some of the same equipment. The channel will get a commission for that, but there's some really great, inexpensive, and simple tools that will help you measure your springs if you so desire. Starting with this really cool force gauge, the way this works is it measures force. When you push and pull on this rod right here, it measures the force, and this is a 5 Newton version, which is about 500 grams or about a pound. It's a very low force gauge, which is perfect for measuring these really soft springs. It's accurate to plus or minus 1% and measures down to 1 gram. So this should be perfect for what we're going to do here. So I built this little table here out of some extra wood I had, and I spray painted it with this Rust-Oleum appliance epoxy. This is really hard. It's harder than paint. It's an epoxy, and it's really smooth and really slick. So you'll see that it works great for this application. Now what I've done here is built a series of little fixtures to hold the different springs, and I'll show you how each one of those works. Also, to make this real easy and real accurate, I found this awesome set of gauge blocks, and it was really cheap. I don't remember how much, but I'll put a link to it. And basically, it's machined aluminum blocks that are super precise. They come in different thicknesses, and you can use them for a ton of things. Anytime you need to space something temporarily or shim something or do a fixture, these things are great. There is a concept in engineering and statistics called Gage R&R. It evaluates the errors introduced when trying to measure something. There are two areas of error: repeatability, that's error in the instrument or the gauge being used; reproducibility, that's error in the person or the operator using the gauge. What's important to know is that variation can come from both me, the operator, and the instrument itself. So for best results, I will take as many measurements as reasonable, then look at the average, standard deviation, etc. to see if my measurements are sufficiently accurate. I'll do all that off camera so I don't bore you, but just know that the more measurements you take, the better your results will be. Also, this applies to your testing in the field. To really demonstrate if a tuning mod worked, you need to test it multiple times. That's repeatability. And if you really want to know if it worked, you'll have a different driver try it and see if that person gets the same results. That's reproducibility. Now let's see some measurements. For a coil spring, I made these fixtures. Now what I'm going to do is put just a tiny bit of preload on that, zero it out, and then in this case what I did is I compressed it 5 millimeters, took a measurement, and then compressed it another 10 millimeters and took another measurement. And that's really super accurate. And I built this little fixture to hold a hairband. And what I'm going to do is give this just a little bit of preload, not too much. You can see that right there. Then I'm going to zero the force. And I'm also going to switch it to grams. So there we are, 0 grams. And what I'm going to do is remove a 20 and measure it again. And I will measure it a few times to check the repeatability. And this gives me a really accurate force measurement for a given distance. Then I'll do it again with another 10 millimeters. And that measurement gives me 3 data points. Now, one thing you might notice is that the force continues to drop a little bit the longer you wait here. That's because the elastic is not as consistent as, say, steel. So it continues to stretch a little bit, the plastic softens, it relaxes, and the force starts to drop off a little bit. Now let's see if these equations correlate with actual measurements. Let's try to test the math for springs in parallel. Just to be as accurate as possible, we'll start by measuring each spring individually. I'm going to give it a tiny bit of preload. Then I'm going to zero it. Then we're going to give it exactly 10 millimeters of preload. .149. I'll write that down. Now let's measure the other one. We'll zero this. .267. So we've measured the springs separately, and now we're going to measure them together. And I want to make really sure that I'm not leaving any gaps in the spring so that both of them have some preload. And it doesn't matter if they're preloaded exactly the same, they just both want to be preloaded a little bit because we're just going to zero out the preload so it doesn't matter. And if you've followed my other videos, you'll know that preload is totally different from spring rate, and what we're measuring here is spring rate. And if I did the math correctly, if we compress this exactly 10 millimeters, we should have 0.416 reading for force. All right, it's wiggling around a little bit. I'm going to zero it one more time. And we're good to go. Dang! Exact. Well, I guess math is real. So now let's combine a compression spring and extension spring and see what happens. Let's start with the fresh measurement from both. We're going to do 10 millimeters of compression because that makes the math real easy. Zero this out. Make sure there's preload, there's no gaps. All right. Going to switch to grams. 161. Back to 0. 161. Let's try the extension spring. Now we're going to start with the 10 millimeter gap in place. Zero this out. Give it a minute to relax. Looks like 58. Double check the zero. So the zero's drifted a little bit. Let's take a second measurement. 75. All right, let's average 75 and 69. So we'll add those spring rates together, which gives us 23.3, and we'll multiply by the 10 millimeter displacement, which will give us a force of 233. Now, if we are modeling this correctly, and we have done the math correctly, when we move this 10 millimeters with the two springs, which should be modeled by the formula for springs in parallel, we're going to see 233 grams. Hopefully. Let's see what happens. $235. That's pretty much as close as you're going to get. The zero has drifted just a little bit because of the nature of the elastic. Let's zero it. Take a second measurement. We're looking for 233, and we're at 238. I'd say that math checks out. Now, in case you weren't persuaded, let's try it again. Let's do a firmer spring and a thinner hairband. We'll start once again with a baseline measurement of each individually. Here we go. This spring is 277. Now let's try with this thin band. Zero out that preload. Take out the 10. Let it relax for a minute. Let's call that 47. Let's check the zero. It's drifted a little, which we've seen. So we'll zero that out. And we're looking at 52. So we'll average that out. So the math says this should be 327. So let's start with it fully extended. Zero out the preload. Again, it's a much stiffer spring and a softer hairband. $325. The math predicted 327. That's as close as you're going to get, within experimental error for sure. Now let's try something else. Let's put the spring approximately where they are both, the preload on each is balancing each other out. So it's right about here, let's say. I'm kind of doing it by feel. And this is where the preload from one spring balances out the preload of the other spring. Now that's not spring rate, that's preload. And let's zero it right here. And let's zero out our, let's make our 0 point here. Okay, let's call that our neutral point. Now I'm going to try one more time. This is from the neutral point, which means this would be exactly at 50% ride height on your vehicle. Let's add 10, see what happens. and we're getting 334. It should be 327. That's definitely still within experimental error. Are you surprised? I can tell that some of your minds might be blown right now. You probably thought that this spring, this hairband was compressing your spring and making it softer, when in reality, you're simply adding the two spring rates to get the new spring rate. This may be very counterintuitive. I don't know if everybody agrees that that's what the result was going to be. You may have thought that taking a stiff spring and adding another spring on top of it would have made this spring softer. That's kind of what intuition would say, but that's not what the math predicted, and it's what we demonstrated experimentally, that when you take two springs, doesn't matter if they're extension springs or compression springs, when you put two springs together, they act as springs in parallel, they obey the equation of springs in parallel, and they add together and equal one stiffer spring. Here's a summary of the measurements I took. It only takes 2 points to define a line, so I only took 2 data points. Since I'm 100% certain that these coil springs are made of steel, they are linear. I only need 2 data points to define the slope and spring rate. Also, each of these data points is the result of at least 3 measurements. Each of these lines represents a different spring. What we are looking at here is the spring rate, or the slope, of each of these lines. I normalized the preload so everything goes through 0, just to make it easier to read. The steeper the line, the higher the spring rate, or the stiffer the spring. You can see that this light blue line is the steepest, which is a low C firm, and these dark blue lines are the flattest, which are the ultra soft springs. Everyone still with me? Now, I didn't know if the elastic hairbands were going to be linear, a straight line, or perhaps a curved line. It takes 3 points to define a curvilinear line. That is a curve that can be described by a simple polynomial. So I took 4 points of data just for good measure. Remember, more is always better, but you can't spend your whole life taking measurements. We got to get out there and drive. Here is the plot of the elastic band data. Again, I normalized the preload so it all goes through 0. As you can see, the response is generally linear, a straight line, which I like. That means the force will be proportional regardless of how much stretch or preload I set it up with. You will see that the spring rate varies even between similarly sized bands. These 2 green lines are both 2mm hairbands, but the spring rate is a little different. If I measured 50 bands, I'd have a much better idea where the average spring rate for a given size falls. Now that we know what spring rates we have for both coil and elastic, we can begin to apply that to our crawlers. Here are all my numbers, rounded off just for convenience. And if you look closely, you'll see that the resultant is just the sum of the coil spring plus the hairband. 27 plus 4 equals 31, for example. Okay, enough nonsense. Let's see why we care about this on a RC rock crawler. Let's break down the math behind adding hairbands or pen springs to a perfectly good shock. Here's your basic shock. The spring pushes it to full extension. Imagine adding an external hairband, which would pull the shock into compression. This type of opposing negative spring pulls the shock back together, wanting to compress it. These springs now have opposing forces that push and pull against each other. Let's just visually replace that rubber band with an extension spring image. Now we've got 2 springs in parallel, even though they are pushing in different directions. This is called the pen spring mod because it uses a good old-fashioned pen spring that just happens to be the right size to slide over most shock shafts. This might be tough to visualize, but this is also springs in parallel. The pen spring pushes on the piston on one end and the shock body on the other end. The external coil spring pushes on the piston at this end and the shock body at this end. I don't care for this mod because it reduces your down travel because the pen spring takes up space and doesn't allow your shock to fully extend. Now this is the part that's really important when it comes to tuning your vehicle. Now let's look at one more thing that will help us better visualize the graph when we put this to paper. So when you find this sort of neutral point, the point at which the spring pushing this way and the band pulling this way balance each other out, if we zero that point, there's a little arrow right here. So when we move in this direction, it says that the force on the gauge is pushing this way. When we go back to 0 and come past that, the gauge says the force is pulling this way. So we've got the 0 point, and you've got opposite forces on either side of that 0 point. Now that will help us to better understand the graph. Now let's take a thicker hairband with the same ultra soft spring. We'll connect that. The gauge was beeping at me because I overloaded it. Now you can see there is no neutral point. It wants to completely bottom out the coil spring in this direction. And that's okay. We'll just zero right there as close as we can. And what we're going to find is that the force is always pulling in one direction. There's no middle point that rests at 0 like we had when the springs were more closely matched. Spring rate is only half the story. I can tell that many of you are scratching your heads. How is my suspension stiffer when the hairband lowers my ride height? Doesn't that mean my spring got softer? The other half of the story is preload. The preload of a negative spring overrides the preload of the positive spring and pulls your ride height down. But that doesn't mean your springs are softer. We've proven that your spring rate goes up. It just means your negative spring preload has overcome the positive spring's preload. When you have a coil spring and you add an elastic negative spring, you end up with a higher total spring rate, even though they are opposing each other. But what does that mean on my rig? Here's how we look at preload. Preload is directional. Spring rate is not. Let's call the direction that the coil spring pushes the shock the positive direction. Hairbands pull in the opposite direction, so let's call that the negative direction. The coil spring is at its highest force when the shock is compressed. The elastic spring is at its highest force when the shock is extended. Let's assume both springs have the same spring rate. When we add these two together, we get a single, steeper spring line. It has twice the stiffness because it has twice the slope. Now, since the springs are equal spring rate in this example, they balance each other out, and they intersect exactly at the midpoint of the travel. If you add preload to the coil spring, it shifts upward. If you add preload to the elastic band, it shifts downward. If you add preload to just one spring, the resultant line shifts with it. In this case, we add preload to the positive spring, and the resultant spring shifts to about 25% compression. This should make sense. A stiffer main coil raises your ride height. The slope of the line stays the same, but the balance point shifts to higher in the travel. Now let's add a whole bunch of preload to the elastic band. Check this out. Now we have full droop. None of this factors in chassis weight, weight bias, or center of gravity yet, or incline and how weight bias changes the steeper the terrain gets. Now keep in mind, this does not hold your front end down. It simply keeps the chassis down relative to the front axle. It keeps your shocks compressed, but eventually your front wheels will lift and the car will flip over backwards. That's just simple physics. In an upcoming video, I will show you exactly how to tune with positive and negative springs to maintain full articulation and keep the chassis down on climbs. Here's a teaser. Don't use two springs on top of each other. Pick one or the other. Either a positive or a negative spring, not both. Pick the right spring rate. Personally, I run no coil springs, and custom low spring rate negative bands with high preload. So what did we learn? 2 springs equal a third spring. That third spring has a higher rate if it's in parallel. Springs have the same rate in compression or extension, and math works.